Good afternoon, chemists. Announcement, I just posted the information about the midterm 3 review session. So it'll be on Tuesday at 6 p.m. like it typically is. All right, and so our exam is during class on Thursday, so a week from today. My plan is to finish up chapter 9 today, and that will conclude what is on midterm 3, so chapter 7, 8, 9. And then we will spend all of Tuesday doing review. Tuesday in class doing review, and then we'll have the review session, an additional one in the evening. How does that sound? Good. All right. Okay, so let's finish. All right, so we left off talking about Le Chatelier's principle. So it sounds, foreign, French, but really all Le Chatelier's principle is talking about is the idea is we have a reversible chemical reaction. And if we make small changes to it, so if we have a reaction that's already at equilibrium, if we poke it, all right, if we poke that equilibrium, it's going to respond to us adjusting it. So that's this whole idea. And I like to think about it as a kind of like a seesaw. All right, I haven't, ridden on one of those in years, but the idea is if you push the reaction one way to one side, in order to counterbalance it, it's going to kind of respond in an opposite direction in order to get back to equilibrium conditions. So here's one example. Basically how a change will be worded. I'll say, okay, given this chemical equilibrium, so nitrogen plus 3 H2s gives 2 ammonias, NH3. I would say if this reaction's at equilibrium and I, let's say, add more ammonia. If I add more ammonia, right, so which way is ammonia? Okay, so I kind of like add more stuff to the product side. Okay, and you think about your seesaw, how can that reaction adjust itself to get it back to being at equilibrium or normal? You'd think, oh, the reaction has to move in this direction. What is this direction? Left. It has to move left, back to the reactant side in order to get it back into equilibrium. If we added more ammonia. Or in this case, it says, well, what if we remove something? What if we remove one of the reactants? In this case, H2. So if we remove H2, we kind of lighten the side on this on the reactant side. So in order for the seesaw to equilibrate itself again, we have to again shift the reaction back to the left, add more H2 to kind of replace what we took away. Does that make sense? So in the processing, Le Chatelier's principle, we'll only talk about it conceptually. We won't really be using numbers here at all. We'll just be thinking, hey, if I make these changes, how will the chemical reaction respond? And if you think seesaw, you'll get it right most of the time. All right, so let's do some more. All right, think about it. How we will answer these questions is just say, if we make this change, so all of them are numbered here, if we make these different changes, how will the reaction respond? Will it move to the shift to the left or shift to the right? That's how we'll answer this. So let's say we increase the concentration of N2. All right, if we increase a reactant, which way will the reaction go? It will go to the left or to the right? To the right, right? Yeah, so if we add the reactant side, the reaction will proceed this way. So we increase, think about that, we increase N2, so the reaction will shift to the right in that case, so it'll shift to the right. Because we're adding more reactants in that case, so we need to kind of consume some of those reactants, push it towards the products. All right, so the next one, what if we decrease H2 concentration? All right, so we're decreasing H2, we're taking some reactant away. Which way will the reaction go to kind of replace the H2 that we took away? The reaction will go this way. Yes, back to the reactant side or to the left, All right, let's say some NH3 escapes from the reaction vessel. If NH3 escapes from the reaction, are we increasing or decreasing the NH3 concentration? Decreasing. So it's just a different way to say it. All right, so if we decrease NH3 concentration, how's the reaction going to respond? It's going to move that way, right? Yeah, so we're kind of removing NH3, so the reaction has to move to the right to compensate for what was decrease there. So it goes to the right. All right, this one's a little bit different. The pressure of the reaction vessel doubles. The pressure doubles. This one's a little bit tricky. So I want you to note here all of the reactants and products, they're all gases. Okay, so they're all gases. So if we think about it, if the reaction, the pressure inside the vessel doubles, the reaction, the equilibrium wants to relieve itself, right? So we need to think about it. What side of the reaction will help the reaction relieve the pressure, the increase in pressure that we put on the reaction? Yeah. Why the product side? Yeah, I think that's a great inference there. There's less on the product side. So my key word here is I said, okay, the reaction increased pressure. In order for the reaction to go back to equilibrium, it wants to relieve that pressure. So we want to go to the side of the reaction with less gas. So in your case, you said that there's just one NH3, but there's actually 2 moles of NH3 on the product side. But how many moles of gas total are on the product or on the reactant side? Yeah, 4. So in order for the reaction to relieve itself of that increase in pressure, it's going to move to the side that has less gas particles, which in this case is the product side. So do you see that? Okay, so another way I could word that last problem, and we would have the same answer. So the answer is to the right. Whoops, to the right. And I'll say because there's less gas. Less gas. I could reword this question. I could say, what if the reaction vessel, the volume decreases? What if I have the volume? That's another way to have the exact same answer. Because if I have the volume of the reaction vessel, won't the pressure go up in that case? So in that case, we're just kind of applying the idea of Boyle's law. If we squeeze all the gases so they're closer together, we'll increase the pressure also. And so applying Le Chatelier's principle, the reaction wants to relieve itself of that increase in pressure, so it will do that by moving to the side of the reaction with less gas particles. All right, how's that? Good? Good. So lots of different ways to ask questions regarding Le Chatelier's principle. Okay, so something we've kind of ignored about chemical equilibrium, and like all chemical reactions, is that energy is involved in chemical reactions. We recall that? Chapter 4, there's energy involved. We typically talk about like exothermic or exothermic reactions, whether heat is produced or consumed during a chemical reaction. So we can apply that concept of heat involved in a chemical reaction also with Le Chatelier's principle. And simply how this works is we need to recall our definitions of exothermic reaction. So in this case, if I tell you that this reaction is exothermic, all right, so NH2 plus H2 gives us ammonia. If I tell you that this reaction is exothermic, us as the surroundings would observe this reaction, that heat is emitted, right? That heat is given off during this reaction, so heat is a product in an exothermic reaction. We recall that? Yeah? So if I, using the same ideas of Le Chatelier's principle, like on the last slide, if I add heat to this reaction, if I increase the pressure, increase the temperature of this reaction, treat heat like a product or a reactant like we did in the previous slide. If we add heat to this reaction, which way will the reaction go? That way, right? It's just like if we said we would have added NH3 and the reaction goes this way. If we add heat in the form of temperature, increasing the temperature, the reaction also goes to the right? Yeah, to the reactant side in that case. So we have to kind of use our intuition and think about, is this a exothermic reaction or endothermic reaction? Is heat a product or is it a reactant? And then whether a question says, are we adding heat, are we increasing temperature of the reaction or decreasing the temperature of the reaction, kind of treat it like we would any other substance, and we can predict the direction it goes. So if we heat the reaction or we increase the temperature of the reaction will go to the Left, right? Left. So I got it wrong before. Wait, left. Yeah, I'm not good at my lefts and rights. Also because I'm facing you guys this way. So give me a break. It goes to the left or to the reactant side. If the reaction is cooled, are we adding heat or removing heat? Removing, so you're just essentially taking some of the heat away. So the reaction's going to move this way, to the right. Yes, that is to the right. Okay, so we're gonna decrease the temperature of the vessel and it's gonna go to the right in that case, all right? All right, so you just treat heat as a product or reactant just like you do the other substances. But the trick is here, in this reaction, I told you where heat is on the reaction, but I could have easily, given you this reaction, told you, hey, this is an exothermic reaction, and you would have to know what side heat has to be on, all right, in order to answer questions that relate to changing the temperature of the reaction vessel. All right, so kind of putting it all together. This is a lab that we do in 1210. I don't know if you guys, they do it anymore, but I really like this lab because there's really pretty colors, okay? And so here's a chemical equilibrium problem. Equation right here. We have a cobalt compound. This is why I'm an inorganic chemist. I don't like living things. I like metals because metals are pretty colors. So these are metals, right? The cobalt complexes. It's a very beautiful blue color, very beautiful pink color. So that's why I became an inorganic chemist for very vain reasons because of the pretty colors. So anyway, we have, what I want you to see is that there's an equilibrium, okay? On the reactant side, we have a complex that's pink. On the product side, we have a complex that's blue. So I give you a picture here that I tell you, okay, if I put this reaction that's at equilibrium and I put it in a hot water bath, it turns blue. But if I put that same test tube in a into a cold and ice water bath, it turns pink. From that information, can you tell me, is this an exothermic reaction or an endothermic reaction? So it's just like what we did in the previous question, right? Where I said, okay, this is an exothermic reaction, you add heat, it shifts this way. But now we're kind of working in reverse. I'm showing you the observations, and from these observations, we should be able to predict, based upon Le Chatelier's principle, which side of the reaction heat is on. So based upon this data, heat is on what side of the reaction, reactants or products? Yeah, see, even in 1210 there, it's like 50-50. Okay, so let's break it down. Okay, so in the hot water bath, what substance is dominant, the blue or the pink? Blue. So when we add heat, the reaction goes to the products to the right. So which side is heat on? The reactant side. Do you see how we got that? So is it an exothermic reaction or an endothermic reaction? Endothermic, all right? So there's definitely some critical thinking there. That's like a higher level question, okay? Definitely higher level, because it's like even me, I can't just look at that and be like, yeah, it's endothermic. I would have to like write it out and think about, okay, which side is heat on to make it consistent with the picture that we see. So it's endothermic. So here, yeah, so pink, because if you think about it, heat, if I put heat here, let's see if this is consistent with our idea. If we increase the temperature of the vessel, it turns blue. It goes to the product side, right? But if we cool it down, if we cool the reaction down, we are actually removing heat. So if we remove heat, the reaction shifts to what direction? To the left, right? To the reactants side, and the reaction vessel turns pink. Is that consistent with what we see? Yes. This is so cool to do this in lab, all right? Because you can do it forever. You can just stick the thing in the hot bath and then stick it in the cold bath and it turns pink. You stick it in the hot bath and it turns blue. Pink, blue. You just do it forever. It goes forever, all right? I really like that. I like that, all right? So it's not, it kind of is counterintuitive, right? We think of chemical reactions as like finite, it blows up and it's done. But no, with chemical equilibrium, it's a little bit different, right? And so you can keep reversing the reaction based upon if you're adding heat or not. It's really cool. Maybe maybe I can see if I can't get the demo team to do it, and we can do it. I'll say half of the 1210 students, they get this wrong too. All right, so the idea is putting heat on the right side that is consistent with what we see. All right, so that's Le Chatelier's principle. Okay. So we can also apply the idea of chemical equilibria. So we looked at Le Chatelier's principle. All these reactions we're looking at are reversible. So the idea, was it in the beginning of this chapter? Yeah, we talked about acids and bases. Strong acids and strong bases, but we also have weak acids and weak bases. So the reason we call them weak acids and weak bases is because they exhibit weak electrolyte characteristics. And so when something is a weak electrolyte, we use this double arrow. That's the big difference between strong electrolytes. Strong electrolytes, when they dissolve in water, you have just a straight arrow, and all of the ions dissolve into, or like the ionic structure dissolves into ions. But when we have a weak electrolyte, only some of it goes forward. Doesn't that kind of sound like chemical equilibrium there? And it's because it is. Weak acids and weak bases do exhibit chemical equilibria. And so here is the equation for the weak acid, what is this? Acetic acid. Okay, so when we add acetic acid into water, it's one of our weak acids because it's not one of the strong six. What happens here, and I mentioned this before, is that only some of those protons come off of the original acid. So we can see this as an acid because what is happening here is that acetic acid is donating its proton to water. So that water is grabbing that hydrogen ion. So the acid is donating its proton. Water here is acting like a base, and it's accepting the proton in that case. And we form the acetate anion and hydronium. So this is essentially H+. That's what makes it acidic. So this reaction only happens partially. If you look at a solution of acetic acid, you will see some neutral molecules that you have on the left side of your chemical reaction, and you see some ions that are on the right side. You see both, and that's what makes it a weak acid and a weak electrolyte. So since this is a chemical equilibrium, we can also write a K expression for this. Right? So remember how we write K expressions. We take anything that has a concentration and we put products over reactants. So when we do that, we take the products. So in this case, it's the concentration of the conjugate base right here. So that's our conjugate base. All right, and then here is the H+, the acid that's kind of given off from our acid. Those go on the top. And then our original neutral acid goes on the bottom, whatever that concentration is. Why don't I include water in this expression? Yeah, it's a liquid, so therefore it doesn't have a concentration, right? Because all of these like brackets mean concentration of that. Water, because it's a pure liquid, and really there's just so much of it that its concentration rarely changes, right? So we don't include it in our expression. So the big idea in this slide is that, I've kind of built you up to this. We talked about strong acids, weak acids. We talked about chemical equilibria, and now putting it together, weak acids are reversible reactions. They are chemical equilibria as well. And so you can look up K values for different acids, for different weak acids, and that will tell you what side of the reaction is more dominant. So let's think about it. If we have a really large K value for an acid, what side of the reaction is more dominant? It would be, so if we have a really large K value, then this side, the product side, would be more dominant, right? Because it's a large value. Versus if you have a really small K value, then this side, the reactant side, is more dominant, all right? So all those rules we talked about before still apply. And specifically here, we're talking about weak acids and weak bases. And I just already said that. So these K values for acids specifically, we call them K subscript A values. A meaning acid. So it's a K value for a weak acid. That's specifically what it means. So the trends that we see here is that the larger the K value, the stronger the acid. The stronger the weak acid, the larger the K value. Because if we recall what that K value means, right, it's products over reactants. So if we have a large K value, there's a ton of products. And if we look back at the product side, this reaction, if we look at our K value, if we have a lot of products, then we have a lot of H3O. We have a lot of acid present. So that kind of makes sense, right? A large K value means we have a lot of products. We have a lot of this floating around in solution. That's what makes it acidic. All right, so yeah, what we see here, K value means products are favored. Large Ka mean lots of H plus because that's the product, and we call that the stronger acid. So here's some examples of K values. All right, so here, really large K, so they're small numbers. These K values are pretty small. All right, so what you see here in this last column, that's what I want you to kind of focus on right now. 1 times 10 to the negative 2 is 0.010, right? Versus something like the Ka of acetic acid is 1.75 times 10 to the negative 5 instead. So that number would be 0. And then a bunch of zeros. So 4 zeros, 1, 7, 5. You probably can't see that. Change that color to something else. There we go. So you can see that for hydrogen sulfate ion, based upon this chart, it has the larger Ka value, okay? Because the exponent on the scientific notation is a smaller negative number, so there's less zeros in the number because these are all really small numbers. So that K value is larger than, let's say, acetic acid, which is a weaker acid. So the larger your Ka value, but again, it's kind of, it can be tricky because these Ka values are really small and they're shown as scientific notation. You'll just have to know that those Ka values are larger there with those less negative scientific notations. So we see that? See that? Okay. All right. So the top ones here are our strongest weak acids within there. And then we will talk about our pKa's in a little bit and how that relates to that. And so what these Ka values mean, so what this means is that we take this formula that's associated with it, and we can write the acid dissociation chemical equilibrium. We essentially write, okay, if we rip off one of those H pluses, form the conjugate base, what is that chemical reaction? I think that's what I want to talk about here, how to kind of write an acid equilibrium expression. So when we throw an acid into water, that H plus will come off. The Ka tells us to what extent it comes off, but we should be able to predict the products here. So you can take an acid and you write what's called the conjugate base. So what that means is you just take off a H plus ion in that case, and whatever that is, that substance is, we call the conjugate base. So let's kind of look at our acetic acid example right here. So that's our acid, acetic acid. That acid loses this H plus. And so when we lose that H plus, we can rewrite that whole chemical formula without that H plus. But note that, see, there's a charge there. It's O minus, all right, because H plus is positive. So that H plus goes to water, all right, and so now we have H3O plus in this case. So in this case, here's our acid. Here's our acid, our acetic acid, and our conjugate base is just that acid without an H plus. That's essentially what it is. And we can actually do it in reverse for water as well. So H2O in this reaction is acting like a base, a Bronsted-Lowry base, because it's accepting a proton, right? So water is acting as a base, so instead of losing an H plus like our acid did, water is going to gain an H plus. But when water gains an H plus, it's H3O, but now the charge is plus because hydrogen ion is a cation. So that's what you see here, that these two go together. All they differ by is an H+. And water here and its H3O plus counterpart also a pair because they just differ by an H+, right, in both of these examples. Yeah, so there we go. Are we going to predict some? Yes. So in the next slide, let's predict what is the conjugate. Oh, wait, no, we already did this. Conjugate base of acetic acid. So let's pretend acetic acid was our previous example, but let's do it in its like formula form. So acetic acid is like this. All right, that's acetic acid. And if it's asking, let's write the conjugate base of acetic acid. Your strategy here is, okay, the acid and the base form, they're related by an H+. So to make the conjugate base, we just remove an H+ from that formula. That's it. And that's how we write the conjugate base. So yeah, my strategy here is remove an H+. So the question is, which H+ do I remove? Do I remove this one, or do I remove these ones? We remove the first one because the acids, typically when we write acids formulas, the most acidic proton is typically written first. So this is the hydrogen that we take. So when we rewrite the base form, we're just going to rewrite it without it. So C2H3O2, but now the charge is what charge? If we're removing, so we're subtracting an H+. If we remove a positive charge, then what's left over is a minus charge, a negative charge, all right? So that is our conjugate base here for acetic acid. What about, let's write the conjugate acid of water. So when we wrote a conjugate base, we removed a proton, removed a hydrogen. So if we want to write the conjugate acid, what we do is we add a H+. So when we think about water, H2O, when we add an H+, it becomes H3O plus in that case. So there we go. So that would be the conjugate acid of water, where we add an H+. And so see how in both of those examples how the forms are related just by an H+. All right. So here's another example of an acid-base pair. Looking at it, so here we have an amine. Okay, this is a base. All right, so we have that nitrogen is pretty basic and it can pick up a proton. So if this is the base, if we want to draw the acid, the conjugate acid, we add a proton, an H+. So the new substance that we make is just going to be the same formula with an extra H. An extra H, so instead of NH2, it's NH3, and it becomes plus. So that would be our conjugate acid. Yeah. Usually, yeah. Oh yeah, this example, it's not. Well, this isn't an acid, right? This isn't an acid. This is a base. Yeah. Okay. So there's our base. And water is acting as an acid here. And then and I think, yeah, that's right. So how these two formulas are related is that the conjugate acid has an additional hydrogen and it's positively charged. All right, so let's do some other ones. Let's write the conjugate base of hydrofluoric acid. So there's kind of two questions embedded here because one, I don't give you a formula. So you have to know or figure out what that chemical formula is. So hydrofluoric acid. I always remember the names, the longest names are the simplest formulas. So how we name acids is we identify what is the anion that the H's are attached to. And so hydrofluoric acid implies that it's a fluorine, but it's simple. It's just F-. It's just fluoride that typically exists like when it's attached to an ionic substance. So hydrofluoric acid is F-, but then we just add enough hydrogens to make it charge neutral. So hydrofluoric acid is just HF. Or I like to just memorize, like hydrochloric acid is HCl. And so anything that sounds like that will have a similar formula. So like hydrobromic acid, HBr, hydroiodic acid, HI. That's how I memorize it because I'm lazy. All right, that's not my answer, right? So I just identified what the acid is, but we want to draw the conjugate base. So if we want to draw the conjugate base, are we going to add add a hydrogen or remove a hydrogen? Remove, yes, remove. We're going to remove a hydrogen. Okay, so we're going to subtract or remove an H plus from this formula. So when we do that, our conjugate base is going to be F minus. Yeah? All right, so next one. What is the conjugate acid of NH3? So, cool, I give you the formula here. So NH3 is a base. So if we want to draw the conjugate acid, are we going to add or remove an H plus? Add. We're going to add an H plus. So if we add an H plus to NH3, it becomes NH4 plus. Yeah, so do note, like when we're doing this adding, removing hydrogen business, you're adding, removing the hydrogen and changing the charge. All right, so you got to remember those. All right, so those are questions concerning conjugate acids and bases. Just know that they differ by one hydrogen or hydrogen ion in this case. They all differ by one. All right, so let's keep going. Because let me just do one more example. Okay, so let's do H3PO4. Does anyone know the name of that? Anyone know the name of that? PO4 is what anion? Phosphate. So 8 becomes ic acid. So this is just phosphoric acid. And again, longer the name, shorter the formula. So longer the formula, like in this case, because it's a polyatomic, the shorter the name. So it's just phosphoric acid. All right, so in this case, this is an acid. So if we want to make the conjugate base form of this, we just remove a hydrogen plus, right? So if we wanted to do that, if we removed a hydrogen plus to make the conjugate base, it would be H2PO4 minus, right? But the question is, can this substance lose more hydrogens? Yeah, it can. All right, so these two are conjugate acids and bases of one another. It's a conjugate acid-base pair. But then this substance can also act as another acid. So we can lose an additional hydrogen, can't we? So if we lose an additional hydrogen plus, it would become HPO4 2 minus, where we lose an additional hydrogen. So then these two are a conjugate acid-base pair. Can we do it again? We can do it again. We can lose another hydrogen, proton in this case. So if we lose another one, it becomes H, or no H. It just becomes PO4 3 minus in that case. And so with those last two, here is another acid conjugate base pair. All right, so the two that are next to one another are related. All right, but this acid H3PO4 is not related to PO4 3 minus. They are not acid base pairs because they differ by 3 protons. They only can differ by 1 in those cases. Right? Okay, so yeah, in general, what we see, because we talked about acids, the higher, right, the larger the Ka value, the stronger the acid. But we know acids can lose their protons and we can draw the conjugate base. So what we also see is if we are working with the conjugate base of an acid, it actually has opposite properties of that acid. So in general, what we see is that the stronger the acid, the weaker the conjugate base. That's typically what we see. So for example, like HCl is a it's a super strong acid. It's not even considered a weak acid. It's just a strong acid. The conjugate base of HCl is what? So to make a conjugate base, we add or remove a proton. We remove one. So HCl, hydrochloric acid, is just Cl minus, yes. Cl minus is a very, very lousy base. It's super bad because really it's just salt. It's like part of salt. right? So it doesn't do anything. It doesn't act like a base. It doesn't act like an acid. It's a very lousy base. So the stronger the acid, the weaker the base. So therefore, the weaker the acid, if we take the conjugate base, it's actually a pretty strong weak base in that case. So we have like opposite personalities here. And that's very interesting and useful to us as like biochemists, as organic chemists, being able to kind of make that relationship and see how a conjugate acid and its an acid and its conjugate base are related based upon their strengths there. We won't ever look at it numerically, just kind of think about it conceptually in this case. All right, I think we already talked about we did this. Writing products for weak acid base equations. The whole idea is that when you have an acid and you want to draw the conjugate base form, you just remove a proton. That's it. And so you recall that that proton is a hydrogen, but also a positive charge. So we need to make sure that the products that we write are balanced. So here, we already kind of did this, but let's write the equilibrium equation for the weak acid phosphoric acid. We just did that, but let's just do it again. So H3PO4, all right, aqueous. Let's write the equation. So the first thing, this is an equilibrium. So what type of arrow do I use? Double arrow. So you do not write this kind of arrow. Don't do it. Okay. You do the double arrow. So there we go. There we go. All right. So we want to indicate that this phosphoric acid is acting like an acid. So it's going to lose just one H+. That's the key detail here. It doesn't lose all three at the same time. It just loses one. So we can write that one H+ right here, okay? And we can just say aqueous or whatever, okay? And then we write the conjugate base in that case. And when you see it all together, you'll see how it's charge neutral and how all the atoms are balanced. So the conjugate base in this case would be H2PO4 minus aqueous. And so if you kind of look at both sides of the equation, just like when we've balanced chemical equations before, it's charge balanced because H+ is plus and the other part of the phosphoric acid is minus, and all the atoms are balanced as well. So that's how we write it. And you can also write the Ka expression for this as well, right? The Ka expression for this would just be products over reactants. So we would write H+, the concentration of H+, times the concentration of H2PO4 minus over the concentration of H3PO4, concentration of that. All right, and so I would say the big takeaway here for writing these equilibrium equations for any acid, it's that you're just taking off one proton, because it can be tricky here. This acid has multiple H+, so I think the common mistake here would be to rip off all of them at the same time, but that doesn't happen. Okay, so are we bringing it together? Yes, we're bringing all of this together. So we can kind of see the idea here that this is an equilibrium equation, that we have this equilibrium equation, we have the double arrow. We can also apply the idea of Le Chatelier's principle to this, and that's what happens in our bodies. So when you take biology and you think about, they say, oh, humans, our bodies are big salt bags, we're big buffer bags. Basically what that means is that we have these weak acids and weak bases in our body, that we can perturb our systems a little bit. All right, these, since they're weak acids and weak bases, they have equilibrium. So if we perturb these equilibrium a little bit, our bodies will respond to them. So this is an example of a weak acid base equilibrium that has to do with hemoglobin. Hemoglobin is part of our blood, and it's what transports oxygen from our lungs to different parts of our body. But this equilibrium, you can tell it's an equilibrium because it has a double arrow, follows Le Chatelier's principle. Right, so this form of hemoglobin, H, where hydrogen is attached to it, a hydrogen plus instead of oxygen, is what we call the deoxygenated form of hemoglobin. It doesn't have an oxygen on it. But then the other one on this side of the reaction, HB, which stands for hemoglobin, with O2 on it, stands for its hemoglobin with an O2 attached to it. all right? So we can see how Le Chatelier's principle works, because when we think about it, when hemoglobin travels to our lungs into like those little capillaries, what do you think the oxygen concentration is in our lungs? Is it high or is it low? In our lungs, when we breathe, oxygen concentration is very high in our lungs. So, based upon Le Chatelier's principle, when we increase the concentration of O2, which way does the reaction go? That way. We make what form of hemoglobin? The form that has the oxygen attached. So we're using Le Chatelier's principle. You are right now just sitting there breathing and existing. That when we breathe oxygen, hemoglobin goes to our lungs, the increase in O2 pushes this equilibrium to form more of the hemoglobin oxygen complex to go off into different parts of our body, into our tissue, to deliver the O2 where it's needed, all right? And that's because there's high concentration of O2 in our lungs. Okay, so high O2 concentration in our lungs. If we think about our bodies, all right, like our tissue has very low concentration of O2. Basically, all the oxygen is near our lungs. So our bodies have the tissue in our bodies have low concentration of O2. So when you think about it, if you decrease the amount of O2 in your system, right, like you would see in the tissue, which way does the equilibrium shift? If there's low oxygen concentration, it goes that way. So what happens is when your hemoglobin travels to parts of your tissue that have low oxygen concentration, Le Chatelier's principle says, hey, rip off that oxygen molecule because we're pushing the reaction this way. All right, and so that's essentially how oxygen transport happens in our bodies, and it's based upon chemical equilibrium and Le Chatelier's principle within that. And then once that hemoglobin that doesn't have the oxygen attached to it, it'll travel back to your lungs to grab another oxygen because of Le Chatelier's principle, and then it'll travel back to other places, and it'll drop off that O2. And it drops off because of Le Chatelier's principle and chemical equilibrium there. Okay, so there we go. All right, so that's hemoglobin. That's just kind of like a side story in applying the idea of Le Chatelier's principle. But now let's go into the idea of water. We do have a little bit more calculations that we have to do within this chapter, and this will help us get there. So water. When we think about water, we just think about like H2O. But I've been lying to you all this time. Water actually does undergo some chemical reactions in a pure solution or a pure sample of water. Oftentimes what happens is that water can self-ionize itself. Because remember we said water, H2O, can act as an acid and a base. It can accept a proton and it can release a proton. So, or donate a proton. So water can do that to itself. So what happens is that one water molecule will give up a proton, so act as an acid, and the other water nearby will act as a base and accept it. And so what we get over here are an OH minus group and an H3 plus group. So this is called the self-ionization or auto-ionization of water, that this happens in water just spontaneously. So just based upon this equation, we can write the K expression for this chemical reaction. So how can we do that? K equals products over reactants, right? Anything that has a concentration. So what goes on the top of this K expression? The products, right. So the product that we see here is OH minus. So K in this expression is OH minus concentration times concentration of H3O plus, or H plus, whatever, you know. Is there anything in the denominator? No, there's not. So you'd think, oh, but there's two H2Os, but water in this case is a liquid, so we don't include it in this expression. So this expression is very useful to us. I said we're calculating K for this reaction, but in actuality, it's so special that we actually call it, we give it its own name. It's called the KW, the equilibrium for water. All right, and so this value, or sorry, this expression has a specific value associated to it. Any sample of water, Kw, which is equal to what we just said, H plus times the concentration of OH, all right, equals 1.0 times 10 to the negative 14. That's very special for water. You need to memorize this. I'm going to put it in red, memorize it. Memorize. So this is a very special K expression. It's specifically for water. And that value is equal to 1.0 times 10 to the negative 14. All right, and we'll do some calculations here. That's why this is important, because it helps us calculate pH of different solutions. All right, I think I have it right here also. So what I just wrote is right here. Kw, which is very special, equals H plus concentration times OH concentration, and is equal to 1 times 10 to the negative 14 at essentially room temperature. That number does change a little bit, but for our purposes, 1 times 10 to the negative 14 is fine. All right, so using this expression, we should be able to calculate either the H plus or OH concentration of any solution as long as we're given one of them. So here, what is the concentration of H plus ions in a solution where OH equals 0.20 molarity? So essentially, we're just going to use our Kw expression. We have that right here, Kw, which we know, it's a number, it's this number, equals H plus concentration times OH minus concentration. So we know the OH minus concentration, that's given. So what we're essentially calculating for is H plus concentration. So at this point, it's just plug and chug. So I'll write out everything. So H plus, right, this is Kw, equals OH minus concentration equals 1 times 10 to the negative 14. Okay, so we want to calculate H plus, and we know OH. So we just plug it in. So H plus equals 1 times 10 to the negative 14 over 0.020 molarity. I'll report this to 2 sig figs. So my answer here is, what is it? 5.0 times 10 to the negative 13 molarity is my acid concentration. We get that? We get that on our calculators? I hope so. So within this part of the chapter, the concentrations that we work with are oftentimes very, very small. So I'm just going to give you a tip for the exam to make sure that you can write scientific notation on your calculators. And especially within this part of the chapter, because we're going to use some other functions like logarithms as well. So definitely practice that. All right, so that's what we get. So now the question is, based upon these answers, right, we have the concentration of H plus, we were given the concentration of OH minus. Do we think this solution is acidic or basic? Do we know? Do we know? What looks more abundant, OH minus or H plus? Which number is bigger? OH minus or H plus? OH minus is a bigger number, right? Although, like how it's written, remember, it's scientific notation, so it can be misleading, but note here that the H plus concentration, it's a tiny number. There's like 12 zeros in that number. It's really small. So there's not a lot of H plus, which is associated with acid. So this is a basic solution. It's basic. And we have another way for us to prove whether something is acidic or basic just coming up. But the whole idea here is that in this water sample, there's an imbalance of H plus and OH minus. So that's what makes acidic versus basic solutions. All right, so we're going to move on to the last part of the chapter here where we talk about pH, the pH scale, and some calculations. So the whole idea, H plus and OH minus is all related to pH. So with that expression that I told you before, our Kw expression, when we have pure water with nothing else in it, the concentration of acid, H plus, is equal to that of the concentration of the base, the OH minus, but that's only in pure water. In the previous example, we added base to it. So what we did was we disrupted that equilibrium, making a basic solution. So what we saw in that previous example is that we added OH minus into solution. So what that does is decrease the amount of acid that's available. So we call that a basic solution. If the opposite was true, if we added H plus into solution somehow, like adding a weak acid, we would make the imbalance the opposite, that there would be much more acid than OH in solution. So we would call that an acidic solution. We only have neutral water when the concentrations of H plus and OH are exactly equal, all right? That's the only time when that water is purely neutral. It's when H plus equals the concentration of OH minus. So we'll kind of prove to ourselves what those values are, all right? What the concentrations of H plus and OH minus are for a neutral water sample. So these two equations you need to memorize as well. It's how to calculate the pH when given an H plus concentration of something, right? So pH, so P is an operation essentially. So pH means negative log of H plus concentration. So P is the operation negative log of. So like for example, you can also calculate POH, which is the negative log of the OH concentration. P bananas would be negative log of the concentration of bananas, right? So that P means just negative log of something. So for example, we saw Ka values, there's also pKa values. So a pKa value is negative log of your Ka value. So whenever you see that a P in front of something, it just means negative log of. And I'll point out that log, when you do it in your calculator, is log base 10, just so you know. It's not, don't use natural log, use log base 10. Okay, so I'll put a little 10 here. So make sure that you can use it. All right, so let's calculate the pH of neutral water. I already told you, when water is neutral, H plus must equal OH minus concentration. So yeah, memorize these two equations and our Kw expression. So our Kw expression is, H plus times the concentration of OH minus equals 1 times 10 to the negative 14. So if we want to calculate the pH of neutral water, remember H plus equals OH minus concentration. I'm just going to call one of them X, right? So if both of those are equal to one another, won't this expression Kw kind of simplify to X squared if they're both the same number? X squared equals 1 times 10 to the negative 14. So this is how we're going to calculate the pH of pure water. We know that these two values are the same number, so I'm just going to call it X squared. So if we take the square root of both sides, X, or the concentration of one of them, it doesn't matter which, X equals 1 times 10 to the negative 7. Make sure that you can do this math with exponents on your calculator for the exam. Okay, so yeah, the square root of 1 times 10 to the negative 14 is 1 times 10 to the negative 7. And so X, remember what we're calculating is the concentration. So the concentration in this case, we'll just say this is the concentration of H plus. It's also the concentration of OH minus, but since we are calculating the pH, we want the H plus concentration. So this is not my answer. I need to convert this to pH now. So to convert that to pH, I do negative log base 10, so make sure you find that on your calculator, negative log of 1 times 10 to the negative 7. All right, so all I did was plug in the H plus concentration into that negative log expression. All right, and so when you do that, negative log 1 times 10 to the negative 7, I get 7. 7. pH of pure water is 7. Is that something we already know? Was that something you already knew? Yeah, but this kind of like proves it, okay? This proves it. So what happens here, because of how the pH scale is in that equation is, the more H plus concentration you have. So if like we had a larger number, like 1 times 10 to the negative 2, the H plus concentration is larger because there's less zeros in like the trailing, the zeros. The pH goes down, right? pH, when you have a smaller number, you have an acidic environment. When you have a pH above 7, that's a basic environment. Do I have that on the next slide? No, I don't. I have more practice problems. Here, so here on slide 39, measuring pH. So anything that's above 7, all right, above pH 7, those are basic pHs, meaning that there's more OH minus in solution than H plus. Okay, and this all has to do with the our pH calculation. You'll see it. If there's like a large amount of H plus floating around in solution, you'll calculate a smaller pH value for acidic solutions when there's more H plus. And so we see things that are lower here on the pH scale. These are our acidic environments. So our bodies operate around neutral. We are not perfect pH 7. I think physiological pH is like, I don't want to say, I don't know. It's like 7.9. I think I just made that up. But it's around 7. Okay, it's not perfectly 7, but it's around 7. And you see here, you can actually have negative pHs. Okay, that's possible because of how our pH equation is. It's just negative log of the concentration of H plus. If you put in a number large enough within that equation, you can get negative pH values, and that's okay. You don't want to be around things that are negative pH values. That's super, super acidic. It's really acidic. Our stomach acid, I think, is like, it's like around 2, I think. 2 is our stomach. Okay, all right, so that's our pH scale. So let's do a couple more pH problems. So keep those equations in mind. pH equals negative log H plus concentration. Then to undo pH, it's your H plus concentration. I think that's what we want to do here. What is the H plus in a solution given a pH? To undo our pH calculation, it's H plus equals 10 to the negative pH. So this equation is just the opposite of our pH equation, but what it is oppositely mathematically. So at this point, it's just plug and chug, right? We are given the pH, so our H plus concentration is just 10 to the negative 4.5. And so if you put that into your calculator, you get a concentration of 3.2 times 10 to the negative 5. Molarity. That's our H plus concentration, right? So just being able to use those equations that you memorize there, right? And again, I like the idea that pH means that you are that's negative log of H plus concentration, that those two things are related to one another. Okay, so this one's a little bit tougher, the second one. We have a solution that contains this concentration of OH. What is the pH? What's the pH of this solution? So again, pH is negative log of H plus. So can I put that OH concentration into my equation? Can I just plug that in? No, I can't. I need H plus concentration. They gave me OH concentration. Dang. How can I get H plus concentration? The other equation I had you memorize? KW, right? KW. If we know OH concentration, we can always get H plus, right? So recall, we have to use two equations here. We need to use the KW expression, which says that H plus concentration times OH always equals 1 times 10 to the negative 14. And then we'll also use our pH equals negative log H plus, right? So thinking about it, we are given OH, so we're going to calculate H plus from that equation, and then we will plug that into our pH equation, yeah? So it's just one tiny little step before you plug it into the pH equation, all right? So that's kind of basically as complicated as it gets within here, but let's do it. All right, so we are given OH concentration, so H plus equals 1 times 10 to the negative 14 over 0.0045 molarity. So that means that OH concentration is H plus is 2.22 times 10 to the negative 12. So just based upon this information, is this a acidic solution or basic solution? Basic, yeah, because there's so much more OH minus. Okay, but let's see how basic it is. So we're just going to plug that number into that equation. All right, and I think the answer is 11.65. That's the pH. So yeah, it's pretty basic. Whoops. Okay. All right, so that's navigating our pH equation. So there's 3 equations to memorize. All right, I already had the supplemental information like printed, so I can't give it to you. So you have to memorize them. They're not that bad, right? They're not that bad. All right, we already talked about this. Oh, it's right here. Look, blood is 7.35. What did I say? Ah, dang it. All right, it was right there. You're probably all laughing at me. Apparently I don't read my slides. Anyway, yes, so their basic regime, acidic regime. In the acidic, H plus is more dominant. In the other one, OH minus is more dominant. All right, okay, let's keep going. All right, so I said before, pH means negative log of H plus. P bananas means negative log of bananas. pKa means negative log of the Ka value. So we're looking back at, is it in the next slide? Yeah, so looking back at this table where I showed you the Ka value. So these are our equilibrium expressions, right? And the numbers associated with them. Large Ka values means that the products is more favored. Small Ka values means that the reactants are more favored. All we're doing when talking about pKa is we're plugging that number into the negative log expression. So a pKa and a Ka are the same, they are trying to say the same thing. Does that make sense? Because it's just the number in the negative log expression. It's the same, it's trying to express the same exact thing. All right, so what happens here, you'll oftentimes see pKa values for different acids, and again, all it's telling us is the relative strength of the acid. But what I don't want you to think, so for example right here, this is acetic acid, so I can tell you the Ka value. If you plug that number into the negative log expression, right, you get a value of 4.76. So what I don't want you to think is that 4.76 is the pH of this acid. That's not what that means. It's not what that means. It essentially is telling us the pH in which the acid and the conjugate base are in equal concentrations. That's what the pKa tells us. So it can tell us a little bit about acid strength within there, but don't think that pH is equal to pKa. That's not what that means. And so what we'll see here is that, like, for example, this acid has a pKa of 4.76, while in this other example, so this is a protonated amine, so it's a different type of acid, it has a pKa that is 9.2. So it has a higher pKa. Its pKa is kind of in the basic regime. That's fine enough when trying to predict acidity strength. So in this example, acetic acid is a stronger acid than our other example, our protonated amine in this case, because its pKa is smaller. But we already talked about this before. Small pKa means that the Ka value is large. So that's what I have on the next slide within here. This table. Okay, we already looked at this, right? Large Ka values are highly acidic. Large Ka values have what? Small or large pKas? Small, because of what negative log means, right? So we're just saying all the same things. Large Ka values, small pKas. So these substances, these acids are strong weak acids versus down here where we have really, really, really small Ka values. These are very, very poor acids, and they have fairly large pKa values. So that's how we navigate that. So let's think about it. Which acid would behave as a stronger acid based upon these pKa's? Acid A or acid B? Which is the stronger acid? Yep, acid A would be the stronger because its pKa is lower. It's lower. It's in the more acidic regime. All right? Okay, so there we go. But again, I think oftentimes what happens is those pKa values just tell us the relative strength of the acids. It doesn't tell us what the pH of these acids are, so don't get those mixed up. The only time when pH equals pKa is when the acid and conjugate base are in equal proportions. So let's look at this example, putting it all together. So we have HCN, which has a pKa of 9.21. All right, here's the equilibrium expression for it. Let's write the Ka expression for this chemical reaction. It's just products over reactants, right? So Ka equals H plus times Cn minus over the concentration of HCN. Whoops, no charge. There we go. All right. So different questions I can ask you. Let's think about this. And really, this is application of Le Chatelier's principle. If I tell you that the pKa is 9.71, what species is dominant at a pH of 7.4? So 7.4, is that more acidic or less acidic than the pKa 9 something? Is that more acidic or less acidic? 7, pH of 7. More acidic. Yes, it's in like the neutral zone, but it's more acidic than 9, right? Because 9 is like straight up basic in the basic regime, but 7 is acidic. So if something's acidic, it has more H plus, right? So thinking about that balanced chemical equation here, if we add H plus to this reaction, which way does the equilibrium shift? This way. So the dominant species at 7.4, because there's more H plus present, is the HCN species. The acid form is more dominant at acidic regimes or at this certain pH. Okay? Yeah? Versus the other way. If your pH is greater than your pKa, so it's more basic, you can think, oh, if it's basic, we're removing H plus, right? We're removing H plus from this expression. If we remove H plus, which way does the equilibrium shift? The other way, right, to the product. So at this basic pH, Cn minus, the negative form of your acid conjugate base, the conjugate base is the more dominant form at basic conditions. pHs that are more basic than your pKa's. And really, it's just kind of like advanced application of Le Chatelier's principle within here. But then the caveat, what pH is the concentration of the acid form and the conjugate base form equal? This happens when pH equals pKa. That's the only time it happens, when those two concentrations of both sides of the equation are equal, your pH will equal pKa. That doesn't happen all the time. Oftentimes, we have to have a buffer system in order to do that. So if I just straight up put HCN into water, the pH that I measure is not going to be anywhere close to the pKa of that proton within there. So I just want you to recognize that. There's a lot of things with P's attached to it, okay? And it can be confusing in that nature. So other things that have multiple pKa values, and it can get a little bit confusing here, are amino acids, and they make up our bodies. They're the building blocks of our bodies. So the important things about amino acids, and we'll talk more about it in next chapter, is that there's specific functional groups there. Functional groups that can have charges, functional groups that can act as acids or bases. So all amino acids have an amine group and an acid group. Amino acid, yeah? All right, and so the amine group has a pKa associated with it. The acid group also has a pKa associated to it. So we've already talked about like removing protons, right? Predicting conjugate bases when we remove protons. So we can do that to these amino acids. So this is alanine, so it's one of the more basic amino acids. So focus on the amine group and the acid group. But in this picture, the acid group isn't a carboxylic acid, it's a carboxylate. And so carboxylate has a fully negative charge associated to it because it lost a proton. And the protonated amine here has a positive charge. So if we think about the total charge of this whole molecule, it's 0. Right? So one side has a positive charge, one side has a negative charge, it's total 0. This has a very special name, it's called a Zwitter ion, and it only happens at very, very certain pHs. And when we inspect the pKa's, we can figure out where that happens. So the Zwitter ion is typically formed if you take the average of your pKa1 and your pKa2. So what you're doing is you look for the pKa of your amine group, and you look at the pKa of your acid group. They have two different pKa's, meaning they have two different pH regions where that proton comes off. All right, so when you have a pH of your solution where it's the average between those two pKa's, you form the Zwitter ion, and that's really important biologically because typically when things are happening in our bodies, they want to be using total neutral molecules, not positively or negatively charged molecules. So that is the pH that we see our Zwitter ion, is the average between the two. And so that's what we see. So here's the first pKa, 2.3. The second pKa for the amine group is 9.7. And so what happens is that the Zwitter ion for alanine in this case is around 6. And it has a net charge of 0 in this case. So when we are more acidic than the Zwitter ion pH, so less than 6, what happens is that everything is protonated because we're in a very, very acidic environment. So the total charge of this amino acid is a +1 because everything is protonated. When a carboxylic acid is protonated, it's neutral. But when an amine group is protonated, is a +1. So total, it's a +1 charge. If we make it more basic, so if we start at 6, we get more basic, what we start doing is ripping off protons. The first proton that we rip off is the carboxylic acid, so it becomes negative. That's when we form our Zwitter ion. But then if we add more base, we'll rip off another proton, this time coming off the amine group. And so when we rip off that proton, this amine group becomes neutral. And that's what you see here. So the total charge of this whole substance when it's in a more basic regime is negative charge. All right, so let's look at an example. So here's a different amino acid. This is valine. It has different pKa values, but we still see an amine group and an acid group. So I'm showing you the two pKa values. There's for the amine group, there's for the acid group. So we know that the Zwitter ion is going to be formed in the average between those two. So we can see probably out of these, which pH, 1.5, 6.5, 10.5, which one will the Zwitter ion be the most dominant species? Which pH? 6.5, because that's closer to the average of 2 and 9. All right, so this is where our Zwitter ion is going to be. Zwitter ion. Closer. Zwitter ion, so that means the charge is 0 because we have a plus and a minus within there. When the pH is very acidic, it means that everything is protonated, and that's exactly the picture that we see here. The carboxylic acid is protonated right there, and we see that the amine is also protonated. So in this picture, what's the overall charge? Plus. There's a plus right there on that amine. When amine is completely protonated, it's a positive charge. All right. So we lose a proton eventually when we increase the pH. We make our Zwitter ion to be charge neutral. But then if we keep making it more basic, we'll remove another proton, another H+, and it will totally be negatively charged because we take off the carboxylic acid proton, and then we take off the H+ off of the protonated amine here. and then it would be a total negative charge. All right, so this is kind of advanced application of the idea of pKa's and pHs and putting it all together within there. I guess we're not going to finish it. Maybe. How many slides? A couple. Okay. All right. So these last slides are just application of the idea of equilibrium. So the last one, which I think is really interesting, is how our blood buffers, how our blood maintains its pH, all right? So this is the bicarbonate buffer system. This is how our blood maintains our pH, because if we drink a soda, if we think about soda as really acidic, you know, our blood doesn't suddenly become really, really acidic and cause a bunch of problems. No, that doesn't happen. And it's because we are big buffer bags constantly trying to maintain that pH. And really all it is application of Le Chatelier's principle. So this is the bicarbonate buffer system. What happens is that CO2 reacts with water and it makes carbonic acid. But we talked about carbonic acid before. It's really unstable, right? So this breaks down almost immediately into a bicarbonate ion and an acid instead. So what you want to focus on is these two halves of the reaction. We have water and CO2 becoming H3O plus and bicarbonate over here. All right, so these two things. That's what we see on the next slide. All right, so our bodies are constantly trying to maintain pH. That's what we call homeostasis, and we use this equilibrium. So this is the same thing: water, CO2, acid, H3 bicarbonate. So what can happen when someone hyperventilates? I didn't know this. I did a lot of reading into this before coming here, but when someone hyperventilates, it can be very destructive on the body, and the reasoning is because it affects the pH of their blood. I just thought that they were breathing crazy. Didn't you think that? They're just breathing crazy. But when someone hyperventilates, what do we ask them to do? Blow into a bag, breathe into a bag. This is why, all right? I think this will blow your mind. All right, so when someone hyperventilates, what they're doing is they're not breathing deep enough, okay? They're not breathing deep enough, and what happens is that they're not expelling enough CO2 out of their breath, and they start building up CO2 into their blood. And when CO2 builds up, CO2 slightly acidic, their pH in their blood goes down. Okay, that's what happens when someone hyperventilates. So what happens is when they do that, we ask them to breathe in a bag. I always thought it was to help them like regulate their breathing, but no, it's actually to recirculate CO2 into their lungs, right? If they're breathing into a bag, right, they breathe out CO2, but they breathe it right back in. So what they're doing here is they're increasing the CO2 concentration. When they breathe into a bag, they add more CO2 into their bloodstream. So if we add more CO2 when they breathe into the bag, which way is the reaction shifted? It shifts that way, right? And so that's what happens here, all right? So the reaction shifts this way. So what happens when we build up CO2 within our bodies, when someone hyperventilates, the blood becomes more, the blood becomes more acidic, and we call this respiratory acidosis. And so we shift the reaction within this way. So this is on the next, sorry, I think I messed up here. I did mess up. All right, so when someone is hyperventilating, the condition is respiratory acidosis. The reaction is pushed this way. Not enough CO2 is expelled from their body, so we have this buildup of CO2, and it goes this way within, and our blood gets more acidic. So here, when someone, when we ask them to breathe into a paper bag, what happens is that it keeps some of that CO2 available for the next breath. So hold on, too much CO2 expelled, shifts reaction to the left, removing acid, raising pH. Hold on, let me think about this. Wow, this is embarrassing. Having breathe keep some, too much. I thought I had this before. My brain isn't maintaining this right now. I'm sorry. we'll have to revisit this, all right? I'm sorry about that. We just have 2 more slides to do, so again, I'll just have to stop here. We will finish the chapter in the first 5 minutes of class on Tuesday, so that means I'll move the homework for chapter 9, but that's not going to help you, right? Because our exam is next week, so if you don't do it, you're just hurting yourself, all right? So I will move that homework assignment. So have a great weekend, everyone.